A very good morning, everyone, and good to have you all back this week.
Good afternoon, sir.
Oh, it's afternoon already? I thought it was a minute to 12. Okay, it's 12. Okay, good afternoon, everyone.
Good afternoon, sir.
Good afternoon.
Yeah, so I think we'll begin. I will try to run through activities and just a little detail about your quiz for next week. I understand we have some direct entry students that are still registering at the moment and may not be able to take the assessment by LMS. So I think one of the class reps sent a message to me earlier. So I'd love us to work out the modality, so we are, for the quiz for next week. So we are able to figure out the platform that will serve us better. Okay, so I'll be expecting feedback from the class so we know the platform to use. Is that okay?
Yes, sir.
Okay. Fine. Just before we pick up things from where we stopped last time, I know we made mention of a whole lot of things. We talked about systems and then made mention of the modeling of LTI systems. So we'll try to wrap up that aspect because I know we made mention of the differential equations. So, but we haven't mentioned the state space representation where we now have to talk about observability, controllability, and stability, which would be very, very, these concepts are very, very important when it comes to controlling your systems, okay? So as you progress in your academic journey, you take some courses in control systems. So then you'll be able to go way in depth. But at this point, it would be good to make mention of some of those details. Then convolution. I understand. I saw a few questions on, I think online, on energy, power, So I want to ask one more time. Do we still have some questions bothering us as far as the energy signals, power signals, neither energy nor power signals are concerned? So we could take it right quick before we progress. Oh, I can see some hands. Okay, please tell me. Timmy Lane.
Morning. Good morning, sir. Good afternoon, sir. Sorry.
Yeah, good afternoon, good day, good evening.
Okay, sir. I was watching your YouTube video and I was in somewhere in energy signal and there was a part where you solved the question about power signal. I don't understand. There was a question you solved on power signal.
Okay, a question I solved on power signal. And
should I restate the question?
Okay, if you can, please.
Okay, the question is x of t is equals to a cos into brackets omega t plus phi close brackets.
Okay.
Then you integrated it in respect to t naught 0 to t naught.
Okay.
And I don't understand the integration parts. Like it looks a little bit confusing for me.
Okay. Okay. You said S of t. Let's see. You said this recap on energy, power, and neither energy nor power signals, right?
Yes, sir.
Okay. You said S of t is the same as A cos omega naught t plus phi, right?
Yes.
Okay. So we want to figure out if this is neither energy nor power signal.
Yes.
Okay. Now, you want to recall your trigonometry? You still remember that? we may not be able to go back to revise all of those. That would take all of our time. So you want to recall your trigonometry and identities, okay? So we'll just try to invoke a few things, okay? And then also check if it's a power signal. Can you recall the formula for power? P is what?
I'm coming.
Okay, I think we just move up 1 over T naught, integral 0 to T naught. That's over one time period. We want to integrate over one time period. Then the modulus of S of T squared dt. Yeah, so, and now we have S of T. So what we need to do is to plug S of T into this, and then we're going to get P being the same of 1 over T naught, integral 0 to T naught is the modulus, right? So
yeah,
A cos omega naught T plus phi squared dt. Okay. Now, you realize that omega naught is not a function of T naught here, but we know that omega naught is the same as 2 pi f naught, which is the same as 2 pi over T naught. So if omega naught is the same as 2 pi over T naught, then it means that T naught will be the same as omega naught. No, it will be the same as 2 pi over omega naught, right? So it means we can replace this with 2 pi over omega naught. We can replace this with 2 pi over omega naught is the same as the time period, right? Is that clear?
Yes, sir.
Mm-hmm. So if that is clear, then you also know that now this will reduce to a squared cos squared omega naught T plus phi dt, right? Integral.
Yeah.
Right? And
yes.
Recall the identity for cos squared omega naught T plus phi from your trigonometry. Yeah. Now, if you recall that, now a squared goes out. Now, this will now be, this now will be omega naught. Recall that this 1 over this will reduce to omega naught over 2 pi, right? That's 1 over this expression. So that a squared comes out. So that will be a squared omega naught over 2 pi, right? Then our limit is now 0 to omega 2 pi over omega naught, right? So we can integrate relative to omega naught T, right?
Yeah.
Mm-hmm. So, but, well, this will be difficult to integrate. So if we recall your identity, well, we don't want to go into all of those rigor right now. So this is out. So we just pull this out, right? We brought this out to this point. So it means we now have a squared omega naught over 2 pi, then integral 0 to 2 pi over omega naught. Then by that identity, we have 1 over 2 into bracket 1 plus cos 2 omega naught T plus 2 phi, yeah, dt. Okay. So now this is going to come out. That will be 1 over 2, right? So 1 over 2 comes out. Yeah. Then you now want to integrate this entire process. Okay. So once you do that over this limit, then what are you going to get? So when you integrate this, what are you going to get? So that's about it. So it's a little extensive. So you want to play with your calculus. So I expect you to go back to your calculus. So those are the things we are going to play with trigonometry. Now, this is just little. Now, now we'll be moving into transforms. So when we move into transforms, then we are going to be playing with more of these. Okay. because in transforms, all we now have to play with will be a lot of trigonometric identities, okay? And you have to integrate, okay? So we want to expand all of these. And then how do we go about that? So now you are going to expand this again, right?
Yeah.
So it's not just one line. So I don't know if that is clear now.
It's a little bit clear, but I can use my basic calculus to solve it now. It's better like this.
Okay. If that's that. So any other I can still see two hands up.
Yes, I have a question on time scaling, sir. Good afternoon, sir.
Okay, so we'll come to the time scaling. Let's sort out the energy, neither energy, no.
Okay, no problem.
Good day, sir.
Okay, good day.
Yeah, my question was, when you're talking about power signals, is your integration meant to be from 0 to T naught, or you can start from a negative T naught value to a positive T naught value?
Well,
then my other
okay, go ahead.
Okay. Then my other question was on discrete time signals, and the question was, can I say the question?
Go ahead, please.
Yeah, x of n is equals to minus 0.5 all raised by n u of n.
S of n,
determine
S of n is equal to minus
0.5
to the n
all raised by n u of n.
U of n, okay.
Yes. So those are my two questions.
Okay, now the point is we are actually trying to integrate over one time period. Okay, so for us to integrate now, when we go by standard, we are actually integrating over the entire length of time frame from some negative infinity to positive infinity. Okay, but with that, we cannot achieve a practical system. So when we now talk in terms of practical systems, we want to analyze the system over the time period. Okay, and we already established that the time period T consists of a combination of time periods, which we may want to refer to as harmonics. Okay, and then we know that the harmonic components are integral multiple of the smallest value, okay, which is T naught, or the largest value, which is T naught. Depends on how you relative to frequency, okay? So if frequency F naught is the smallest value, then T naught must be the largest value, right? Because there's the inverse proportionality, isn't it?
Yes, sir.
And we now realize that the integral multiple of this gives us other values. So we're interested in this value, the smallest frequency value. We are interested in this value, the fundamental frequency for the harmonics, which is proportional to the fundamental time period. So once we are able to do that, then all other analysis follows. So that is why we want to integrate over one time period. Is that clear?
Yes, sir. And there was a point to use 0 to T over 2. So when would you use T over 2 as your limit?
0 to
T over 2.
T over 2. Oh,
yes, sir.
I think to T over 2. I think I'll have to see that problem. Which problem did we do that?
Okay, x of t equals to T u of t.
S of t equal to T u of
t.
Okay. Okay, this is a ramp, right?
Yes, sir.
This is a ramp. So it's going to tilt off to infinity. So it's neither energy nor power signal. And I have to take all my value from negative infinity to positive infinity. So I just took a unit value from negative T over 2 to T over 2, right? Yeah.
Can you also use negative T to T?
Why not? Then you have to scale your time period when you are now resolving power.
I don't get, sir.
Okay, t over 2 minus t over 2 is what? This plus this, that's t.
T.
This one
Yes,
time
sir.
period, yeah. So
Okay, okay.
I'm still working within the one time period frame. So if I should use negative t to t, then that would be 2t. So I'll have to scale, your power, P, is 1 over t integral, right? So I'll have to scale this value so that we'll see fall within one time period. I don't know if that's clear.
Yeah, it's clear, sir. Thank you, sir. Then the second question.
Okay, that's the one on the board, right? So what's it about this? What's the problem with this problem?
Yeah, during the summation, I didn't really understand how you did it.
Okay, during the summation, what summation?
You
We are
know,
still trying to
this is
figure out energy or power signal, right?
yes.
Okay, so what summation are you talking about?
You know, for continuous time signal is integration. Then for discrete time signal is summation.
Yeah.
Yes. So as you were calculating it, I didn't even get the steps.
Oh, you didn't get the steps. Okay.
Yes, sir.
Sorry, Isaac, can you come again? What did you just say just now?
Yeah, for continuous time signal, you use
Continuous time
integration.
signals, you use
You use
integration, and
integration.
for
Discrete time signals, you use summation.
okay, all right, thank you.
Yeah, integration is actually the sum of whatsoever in the continuous plane, right? Yeah, so now we are going to be talking convolution, so we are going to see that. So why sum is in the discrete sense, yeah. I think we mentioned that in our previous lecture as well, right?
Yes, sir.
Okay, so you want us to solve this, right? Okay.
Yes, sir. Yes, sir.
Okay. Now, if we want to figure out, if this is an energy signal, so what's the first thing to do? So tell me, what's the first thing to do?
You use the formula.
Okay, we use the formula. And what's the formula?
Sigma x of n always power 2.
Sigma from n equal to negative infinity to infinity, right?
Yes.
The modulus of s of n squared. This is what we want to do, right? Okay, so we already know s of n. So let us plug that in. So this will give us the sigma n equal to negative infinity to infinity mod minus 0.5 n u of n squared, right? So this negative will be taken care of because of the modulus, right?
Yes, sir.
And now this u of n is something like this. So all values at negative infinity will reduce to 0. So this signal is not going to exist from 0 to positive infinity, right?
Yes, sir.
So meaning we can now rewrite this to imply sigma n equal to 0. So the u of n has been taken care of. We don't want to see that again. So it has altered the limit and truncated the negative infinity by multiplying it by 0. And then our limit for...
Sorry, do you understand what you just did there? That's like when you wrote the function inside the absolute value sign, what did you write on top there? You said it goes from negative infinity to 0.
Okay.
And then did you scale it up?
No, let's clean this. Let's leave that. Let's take it step by step. Okay, now recall your units. We want to resolve this first before we resolve the modulus, right? So we know your unit step function is takes on value of 1 for n greater or equal to 0 and is 0 for n less than 0, right? So the plot is something like this. So this is 0 everywhere. Then this is somewhere to infinity. So, this is negative infinity, positive infinity. This is 0 on the time scale, right? Is that clear? Is that clear? Is that clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now we're going to multiply that by this entire process. So it means that if we multiply this by the entire process, so our limit will also be altered, because from negative infinity, all parameters we have from negative infinity will be multiplied by 0. So our limit will now begin from 0 to infinity, right? Because we have the unit step function. Is that clear?
Sir,
Yeah?
so is it for every unit step function?
That's if the unit step function multiplies your signal. You recall our signal manipulation, you do multiplication. So we are multiplying it by this signal. And this signal takes on values from negative infinity to positive infinity. That's the signal. And now we just multiply this signal by something that truncates. So 0 at this point times all parameters here will be 0, right? Then all parameters here will have value other than 0, isn't it?
Yes, sir.
Exactly. So it means that the energy signal, because we multiplied by a unit step function, will now be rewritten as n equal to 0 to infinity mod minus 0.5 to the power of n squared. Is that clear? So it means that the unit step function has performed this operation on the signal. Okay, I can see one hand up.
Yes, sir. Good afternoon, sir.
Good
Sir,
afternoon.
but I thought for all unit step function, you're supposed to range it from 0 to 1, not 0 to infinity.
No, the magnitude is 1. That's the amplitude. This is 1. The time scale extends to infinity. This is the time scale. This, okay? So the magnitude of this discontinuity, this is the place point of discontinuity. This magnitude is 1, but the signal saturates to infinity. This time axis, positive infinity.
Okay,
This
sir.
time
Okay.
axis
Thank you,
is
sir.
positive infinity. Yeah. So we are not referring to the amplitude. We are referring to the duration, right? The signal duration. Is that clear?
Yes, sir. Thank you, sir.
Okay. So we now have this, but there's something the modulus will do, right? The modulus is going to truncate the negative sign. Recall your mathematics, isn't it? Are we still on the same page?
Yes, sir.
Yes, sir.
Yes,
So,
sir.
Please come again.
So this modulus, when we say you are
Yeah.
taking the modulus of anything, it takes care of the negative. So all negative signs.
Yes, sir. Yes, sir.
Exactly. Yeah. So the energy signal becomes this now, n equal to 0 to infinity, then 0.5 to the power of n all squared, right? So this will now be sigma n equal to 0 to infinity, 0.5 to the power of 2n. Right? Is that clear?
Yes, sir.
Yes, sir.
So,
Yes, sir.
so it's the same as saying n equal to 0, sigma n equal to sigma taking on values from n equal to 0 to infinity. 0.5 to the power of 2 will give us 0.25 n, right? So as we increase the power, this value reduces to 0. So the power of 3 will be less than 0.25 to the power of 5 to the power. So if we increase the power, so if n increases, this entire energy value will reduce to 0. Do you agree with me?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay.
Yes, sir.
Okay. Now, what kind of problem is this? This brings us to series. You remember your series in mathematics. We have series, right? Geometric series and arithmetic series. Right?
Yes,
Do you still remember or you have forgotten?
Yes, sir.
Huh? You still remember, right?
Yes, sir.
Now, what is the sum of, okay, now when we talk about geometric series, how many types of geometric series do we have?
I can only remember two,
Tell us.
Taylor's and McLaurin.
Tell us and what?
McLaurin series.
Okay, but well, what I mean is we have finite,
We have a finite and infinite or
geometric series
divergent.
and infinite geometric series. Arithmetic series also, we have finite and infinite. That's what I mean, okay? Now, we know that this is not arithmetic. This is geometric because it's raised to the power, right? Hello?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay. Infinite geometric series. Okay, finite geometric. Now, the sum, recall, the sum of a geometric series or the sum of finite geometric series is the same as what? We have the first term, 1 minus r to the power of n over 1 minus r. That is when r is not the same as 1, right?
Yes, sir.
Yes, sir.
Now, if r is the same as 1, then the sum will be the same as the first, as n times the first term, right? For finite
Yes,
series.
sir. Yes, sir.
Now, when we talk about infinite geometric series,
Sir.
yeah,
Sorry, sir. If r is equals to 1, you should have infinity. The sum should be equal to infinity if r is exactly equals to 1.
if r is equal to 1, that's 1 minus 1 over, that's 1 to the power of n. So 1 minus 1 to the power of n, n to the power of n is 1. So 1 minus 1 is 0 over 1 minus r. Yeah,
So
then times a.
Yeah, I think you meant to write greater than. So
is r greater than? If r is
Okay.
equals to 1, yes.
Okay, r greater than. Okay, fine. Let's move on. If mod of r is less than 1 for infinity, for infinite geometric series, then the sum, if I'm not making a mistake, will be a over 1 minus r, right?
Yes, sir.
Yes, sir.
And then the other way around, then we will not have convergence, right? Okay.
Yes, sir.
Now, let us come back to our problem, the problem we're trying to solve, okay? So let us wipe this. That's just a quick recap. Okay, let us come back to this. So when this is less than or not the same as 1, then we have this. Good. You will now observe that whatsoever we have here is equivalent to this. So I don't know what we placed in our last solution, you know, but it means that we now have to solve this geometric series. Now, if this, for instance, meaning that this expression, so let me wipe this. If this expression now is equivalent to the sum, taking on values from 0 to infinity, is the same as r to the power of n, then this will be the same as a over 1 minus r for all values of mod r less than 1. Which is sum of an infinite geometric series, right? Like we mentioned, like I wiped, right? That's
Sir, I'm lost, sir.
Recall for infinite geometric series. I mentioned that the sum is the same as A over 1 minus R when R is less than 1, right?
Yes, sir.
Yes, sir.
Yeah, so then this is similar to what we have. So we have this 0.25 to be R to the power of N. Then we have this, right? So the point now is, what is our first term? We already know the common ratio, right?
Yes, sir.
We know the common ratio to be
Yes, sir.
0.25
0.25. Yes, sir.
because R is less than 1. So that informs that, right? 0.25 is less than 1. So we know this is an infinite ratio. Okay? Hello?
Yes, sir. What with you? What with you?
Okay. This condition. And we know this is R going by this,
Yes, sir.
right? Now, if we are together, so it means R is 0.25, which is less than 1, right? Now, what is our first term? What is our first term in this case?
0.25.
Our first term, I mean A. A. What is A?
It's 0.25.
I think
One.
zero.
It's 0.25.
One.
Sir,
0.5.
A is 0, R is 0.25.
The common ratio
A
is
can be
0.25.
0.25.
A can't be 0.25. So what is the first term?
A
I think
is 0.
zero.
One is A is one.
0.5.
A is 0.5.
Okay, somebody said 0.5, somebody said it's 1. Okay,
1.
okay. So the first term is 1.
A is 1.
Yeah, so A is equal to 1, right? How is it 1? Now, when N is equal to 0, when N is equal to 0 at this point, so what do we have? That will be 0.5 to the power of 2 times 0, right? Which would be 0.5 to the power of 0, which is equal to 1. Okay? So that gives us our first term. A is equal to 1, right? From N equal to 0, we get first term, N equal to 1, all the way we progress in that order, right? Is that clear?
Yes, sir.
So I think now we have our solution so that the energy value, E, is the same as sigma N equal to 0 to infinity, 0.25 to the power of N. This is the solution. A is 1 over 1 minus R, which is 0.25, which is 1 over 1 minus this, that's 0.75. So that will be 1 over 3 over 4, right?
3 over 4.
Which is 4 over 3. I'm sure that's what we got, right?
Yes, sir.
Okay. So is it clear now?
Yeah, very clear. Understanding now, sir. Thank you.
Okay. So now that you've got this, then you also want to confirm, okay, if the energy value is 0, then is how about the power?
Since it's a finite number, it's an energy signal.
It's an energy signal. But what if the power of this same signal is not the same as 0? Because the condition is that the power must be 0.
If it's not zero, then there's neither energy nor power.
Well, so oftentimes the best practice is for you to quickly run a quick check. You could do that check. The power is the same as limit n taking on values extending to infinity, 1 over 2n plus 1 sigma 0.5 2 to the n for n equal to 0 to n, right? So this is the same as saying that we take on this limit n taking on extending to infinity. Now sigma 0.5 to 2n, n equal to 0 to n, this is cap n, over 2n plus 1. Okay? So what happens when n tends to infinity? When n, cap n tends to infinity. So when n tends to infinity, this value reduces to 0, right? Because it begins to reduce from 0.5 to 0.25, it begins to reduce to 0, right? So as the numerator reduces to 0, this entire process, now this denominator we extend to some infinite value, right? So 0 over infinity will still give us 0. So the power will reduce to 0. So meaning that the signal is an energy signal. Is that clear? That is
Yes, sir.
Sn equal to minus 0.5 to the n.
Hello, sir.
U of n is an energy signal. Yeah? So tell me.
Yes, sir. Please, sir, I do not know how you got the
Hi, got
value
one.
for the value 1 over 2n plus 1.
No, this is the formula for power in the discrete domain.
Okay, sir.
Yeah.
Thank you, sir.
Okay. Okay, so I think we've cleared all doubts. So can we progress to our business of the day?
Yes, sir.
Okay.
Yes, sir.
Okay. So I know we stopped somewhere. Okay, modeling, LTI modeling, right? So let us quickly run through the LTI modeling system. LTI modeling. Okay. So I recall that in our last class, we made mention that we said that the LTI systems could be modeled using differential equations, right?
So
Model them using differential equations. And when we do this, we now have to develop the general solution to the model. And then this is going to be the sum of the particular solution and the homogeneous solution. And we know that the particular solution is any function that satisfies the differential equation, while the homogeneous solution is the solution of the differential equation with all inputs set to 0. So when we set all the inputs to 0, we solve our homogeneous equation, and then this satisfies the differential equation.
Sorry, sir, can you repeat what you said about particular solutions and homogeneous solutions?
Well, you already played with this when you played with your differential equations, right? I'm just recapping. So
Okay, sir.
we are just applying your mathematics, okay? So I said particular solution is one in which the function satisfies the differential equation. So that's what I said. While the homogeneous equation is the solution of the differential equation when all the input terms are set to 0, right? So we'll get the general solution for that. Well, as we progress in our study, we may run into some problems where we'll have to invoke this. But the idea is, if there's anything you've done in mathematics, this is one good time to begin to apply them. Okay? So if you've ever asked the question, why are we doing all this? Calculus, trigonometry, why? You know? So I'm sure you're beginning to see why. Okay? Because they are very useful in modeling systems, system responses, and the likes. Okay. So another approach is the graphical representation. So we're going to talk about the graphical representation. And then we're going to talk about state space representation, state space representation. So oftentimes we want to leave the state space representation, you know, for, you know, higher studies, but we'll mention it here. We'll try to simplify it this time just to see, but not the details, but at least basic introduction. So that, you know, whenever you see your system of equations, or better still, you try to resolve your circuit analysis, you may decide to address the solution using state space representation rather than using your regular, you know, theorems, the Kirchhoffs and the like. So you still use Kirchhoffs, so the Kirchhoffs voltage and current laws to play with. Those are the basics, and Ohm's law. Those are the basic principles. But talking about the theorems, proposition, nothing, and the likes, you know, you may not want to play with them. You may want to go, you know, you may want to represent the entire system using the state space model, you know, and then solve it. Well, it's fine. So we'll look at those two, then we'll try to play with convolution. Then afterwards, we delve into transforms, okay? And once we do that, I think we are done with the course, okay? Okay, let us look up where you already have this in your notes, so I will not spend so much time on this. The graphical representation of continuous time systems. Let's put it that way, okay? So, well, we address this as the integrator, adder, gain, block diagram. So we have the canonical form, and from the canonical form, we are just able to address, represent other models for which we have been able to derive the differential equation. So, but what I want you to understand here is that we achieve this system of modeling through repeated integration, okay? So when we have the system of equation, or better still, the mathematical model, the differential equation, so we try to integrate over and over and over again till we remove all the derivative terms. And once we do that, we now come up with the canonical form, okay? And the canonical form will now become sigma k equals 0 to n a sub k integral, taking on the values of k, phi of t, the t is the same as sigma k equal to 0 to n b sub k integral s of t dt. So this is the form we actually obtain after repeated integration, okay? So by the time you take the differential equation, we integrate, and then we separate these variables, the output and the input, you know, the state variables and all, we separate them so that y of t is now equal to s of t, And then this is what we get. So this is such that the integral s of t dt taking on values of k is the kth order integral, right? And then we have that the diagram is such that we have the other here. These are the gains. It's another one. Other, then y.
I hear you. You're not muted.
So this is the input s of t. Then we have the integrator here. Then it goes all the way. Then you observe that the gain now points all out. Both of them point out this way, but this time they begin to point in different direction, the integral. And then this goes all the way, okay? Goes all the way. So depending on the order of the differential equation, that will determine what we get. So we have another integral here, for instance, to close it up. Okay. So we have this gain block here and this gain block here. And then all of these then same thing applies here. So when we have a positive, what I call this feed forward or feedback, then this is negative, okay? Negative feedback, okay? So here, this is positive. And recall, these are the coefficients. So this will be 1. Let's change the color. This will be 1 over A naught. Then this is A sub 1, A sub 2 to A sub n. Why this will be this coefficient, the coefficient of x of t. Then this is B naught, but not the inverse. Now this is inverse, but this is not inverse, okay? And this is B sub 1, B sub 2, then B sub n. Okay? Now, A sub k are the coefficients of y. B sub k are the coefficients of x. So at this point, we have the coefficients for higher order derivatives, while at this lower part, we have coefficients for lower order derivatives. Now, this is more like a canonical form, which was derived based on the repeated integration of the differential equation that describes the model. Okay? Now, I think we have a simple example. So let us assume, let's wipe this. So I don't want to get rid of this. So we are still going to use it. So let's wipe this. Okay, no. I think, so let us assume we have, say 6. This is the third order plus 2 So these are differential equations, yeah, minus y plus 3y is equal to 4x dot minus 3x dot plus x. So this is the cube y, the t cube, and this is the squared y, the t squared. This is the y dt. This is the x, the squared x, the t squared. Why this is the x dt, right? So you already know that. So let's assume after repeated integration, this is what we get. So what we are now saying is that 1, so this now 6, this will now be, what we have here will be 1 over 6. Then this will be 2. This will be minus 1. The coefficient, why this will be 3, right? Why this will be 3. Now, at this point, we do not have the third, so this will be out. So we are going to strike this out. So, but we have at this point, so this will be 4. Now this will be negative 3. This will be negative 3. And now this will be the same as 1, right? This will be 1. So we could replace this with just a single line, or we'll place our 1 in there. So it means that we are going to get this part. And then this model will now look something like this, based on this differential equation that describes the continuous time system. Okay, this is pretty straightforward, and we have details in your lecture notes online. But there's something we do not have in your lecture notes online, which is the state space representation. So we have more details about that. So I think in our last class, we just had to mention briefly, but this time we want to provide a little more detail. Okay. State space representation. So when you begin to play with your control theory, probably this year or your final grade, now you're going to come to this, okay? Yeah, so, well, it's another way of modeling your continuous time systems, okay? And we say that a state is any internal system variable whose next value depends on its current value, okay? So when we say state, we say the state of a system. So we say a state is any internal system variable whose next value depends on its current value, okay? So technically, it contains information about how the system evolves in time. So we are really interested in that state, okay? And if we look up an RLC circuit, I wouldn't know if you've gotten to that in your fundamentals of electrical engineering. I know you play with storage devices, and then you play with your RL, RC, which happen to be first order, then your RLC, your second order circuit, because you have LC, two storage devices. So, so I'll just play with that, just a simple analogy anyway. So let's assume we have your RLC circuit. Now, I don't want to use resort to your conventional steady state approach to solving the problem. So I want to solve this problem using the state space representation, because by using the state space representation, I'm able to come up with some matrices, okay? So the matrix that describes the system itself, the system matrix, the input matrix, the output matrix, the feed-forward matrix, you know. So with those matrices, I could tell, or better still analyze especially with the system matrix, I could tell the stability of that system. Okay, so when you hear in your power systems analysis, you're talking about system stability. So those are the things they do. So when you see some matrices of XYZ order, it's just that it contains the information to describe the system, even in electronics and communication, okay? So we don't want to develop systems that are not stable. And we already mentioned the fundamental requirement for stability. We should be able to generate a bounded output for bounded input, okay? And then when it comes to robotics, your space design, your airplane, your aircraft, your rockets, and you know, spaceship and all of that. You know, we also want to check if these systems can be controlled. Can they be observed? You know, observability, controllability comes into the picture. And then the output matrix, the input matrix, and the system matrix now gives us enough information to tell if that design will be controllable or not. You know, if it will be observable or not. So that will now give us enough information to tell if it will be worth designing it or not. So I wanted to get the idea. Now we want to literally, I wanted to literally begin to visualize practical systems, especially the impossible ones. You know, you just design a system that can fly in the air or that can leave the edge space and get into space. You know, you want to launch a satellite in space and you want it to orbit, you know, in a certain orbit, you know. Then you say, you know, now, how are you able to do that? Then you want to launch a missile, you know, things like that. So at the end of the day, the design, the system should be such that it is stable, it is controllable, it is observable, okay? Now, this is what you do in control systems, but interestingly, your signals and systems course introduces you to, or provides the introduction rather, to all of these, your control, your signal processing, analysis, and all of that. Okay, so let us take the RLC circuit, for instance, okay? So we have our signal, which is the voltage source. Let's make it a little clearer. So we have a resistor. We have the inductor, one inductor here, another inductor here. So now we have a capacitor somewhere here, more like a ladder circuit. So we have that, okay, so this is R1. So I have another resistor here. Okay, so this R1, this is L1, this is L2, this is C, and then this is R2. So this is my input signal, S of T. So I want to also measure my output. This time is your voltage, but it's my signal, right? Output voltage Y of T, okay? So this is what I've got. Then say the signal direction, say this flows in this direction, I1 of T, and let's say this flows in this direction, I2 of T, then I think that's that. So we can actually measure, let's say we measure positive, negative V1 of T at this point. So this is what we've got, okay? So now we want to check the state. Okay, so the higher order differential equation that describes the system could be written as a series of either first order, second order, or whatsoever order differential equations. And this will usually include the input, the output, let's say inputs, outputs, it could be multiple, and then the internal states, okay? Internal states. So that's what it is. So now, how many inputs do we have here? How many inputs do we have here? So
Very two, sir.
two inputs. What are they?
One.
Someone said one input, right? So what is that input?
The voltage source.
Yeah.
And that's the X of T. The voltage source.
Exactly. So the input, we have one input. So this is one input, and that is S of T. How about the output?
One of T.
Okay, we also have
Y of T.
output Y of T. So how many internal states do we have here?
Three.
Three, yeah, so it's three. So we have three internal states. So who can tell us what those three internal states are?
The resistor and the inductor.
No, those are the elements.
I1 of T, I2 of T, and V1 of T.
Exactly. I1 of T, I2 of T, and V1 of T. Those are the internal states. Okay? So the first thing is to identify the three state variables. Okay? So once we do that, then we want to derive their relationship. So we have been able to determine, or better still, yeah, we've been able to identify the three state variables. Okay? So these now are the state variables. These are the state variables. State variables. And how do we derive their relationship? So that brings us back to your Kirchhoff's current and voltage laws, okay, which you already know, right? Now, you should be able to write the KVL, KCL for all of these, for I1, I2, and V1, right? Isn't it? So, KVL for I1, so that's going to give us L1, the I1 of T, the T will be the same as negative R1, I1 of T minus V1 of T plus S of T. Isn't it? Right? That's this current flowing this way. Right? Is that clear? Because we are considering.
So how are we subtracting, sir?
The voltage drop. Have you done have you played with KVL, KCL in your fundamentals of electrical engineering?
Yes, sir.
Perfect. So that's what we just did. So let's write KCL at this point. Okay, so let's do that. Can we do that together?
Yes, sir. I1 of T. I1 of T. I1 of T.
So this would be, say, let's say in this loop, let's say the current, this is the current direction, right? So this is already voltage source, that will be negative S of T plus, you know, by passive sign convention, this is positive, negative, right? So that will be plus R1, I1
of T
plus L1, the I1 of T dt, right?
Yes, sir.
plus V plus V1 of T, right?
Yes,
Is
sir.
equal to 0. So L1, the I1 of T plus the T will be the same as, once this crosses the 0 sign, that will be negative R1 I1 of T. Yeah. Then this, it crosses minus V1
V1
of
of
T
T.
plus S of T. That's how we got this, right? That's a KVL, right? So, well, we don't have to start playing with all of those details because it's what you already know, right? So now, if you have some doubt, you want to revert back to the lecture notes on fundamentals of electrical engineering. Okay, so you could play with the videos there to recap your fundamentals of electrical engineering. Is that okay?
Yes, sir.
Okay. Now, if we take KVL, also at this point, this is the current direction. So we're going to have L2, the I2 of T, dt, being the same as negative R2, I2 of T minus V1 of T. And then at this point, this current is going into this node, and this current is going into this node, right? So we now write KCL, right? KCL, the sum of current in the node is equal to 0, right? So current flowing in must be the same as current flowing out. So if that's what it is, KCL at this point, we have C, dV, 1 dt will be the same as I1 of T plus I2 of T. That's KCL, right? So this is coming in, this is coming in, that's this plus this will be the same as the current flowing out, which is this current, the current flowing through this capacitor, right? Which will be this value. Then, now that we have done this, we can equally specify our output, right? Now, the output is the same as the voltage across this resistor, right? And we have I2 flowing through this resistor, yeah? So the output Y of T will be the same as negative R2 I2 of T, right? Because the current flowing is flowing in the opposite direction. This is how the current is flowing, right? And this is positive, this is negative, through the negative, right? So that's why we have negative R2 I2. Is that okay? Passive sign convention? Are we clear? Is this good?
No, sir.
Huh?
Yes, sir.
Okay, yes. So I'll take yes. So now I'm going to wipe this because I don't want to clear the equations. So I want us to, I think I can hear a little background noise. So, okay, I think it's better now. So let us rearrange these equations. Well, you really have nothing to worry about at this point right now, because one thing I would love you guys to know is that the courses you are taking presently, they are all related. All the courses you get to take from your first year to final year are all related. I want you to have that mindset. Only that they cannot all be taken by one lecturer, okay? So they are broken into different modules or courses for you to take. So be rest assured that everything you get to learn in your fundamentals of electrical engineering applies here. And everything you get to learn here also applies there, okay? So it's a continuum, only that, they have been taken by different course lecturers. So, and you have nothing to worry about for now. So, we need the current values in their, well, we want to rearrange the differential equations. Let's put it that way. So for this, the I1, so let's change the color so to make it a little colorful. So the I1 of T, the T will be the same as, so when this L1 divides through, negative R1 over L1, I1 of T minus 1 over L1 V1 of t plus 1 over L1 S of t. So we've taken care of that. So the I sub 2 dt will be the same as negative R2 over L2 I2 of t minus 1 over L2 V1 of t. So we've taken care of that. Now, the V1 of t dt will be the same as 1 over C I1 of t plus 1 over C I2 of t, right? So I also have my output. My output is y of t being the same as negative R2 I2 of t, okay? So we have represented this in a cleaner manner. So I want to wipe all of these. Oh, no. I'm going to wipe this. I want to wipe this. So the next thing now is to invoke the general form of the space-space model. So the series of state equations can now be written in matrix form. So we have, these are the state equations. So we now want to write them in the matrix form. But in the general form is given as this. So let's look at the general form. This is what you don't want to forget. Okay, so x, the first time derivative of x is the same as ax plus bu. Then y is the same as cx plus d. Okay. Now, it could be du or whatsoever. Now, so we now want to define, or better still, describe what we have in this case. Okay? So that, like I mentioned earlier, this now gives us this state space representation of what we have to play with going forward. Okay? And now, okay. And with this, we are able to provide an explanation, okay? So these now are literally the matrices, okay? So I have my x as the state vector in this case, okay? X is the state vector. Then U is the input vector. Y, as we already mentioned, is the output vector.
Output vector.
Then A is the system matrix, which is very important. Then B is the input matrix. Input matrix. My C is the output matrix. YD is the feed forward matrix. Okay. So this describes the state, while this describes the output. Is that okay? Now, now that we have this, we have to represent all of these in terms of this. Now, you observe that the state or the state variables, because these are the state variables, right? I sub 2, V sub 1, okay? Those are the 3 state variables. So, and they are the first time derivative, which is this, okay? So we're going to have this, then all of these are the coefficients, okay? And you observe the arrangement. Observe the arrangement. So this will be I1. Now, let me wipe this so that you observe the arrangement of this matrix form. So now, so I want to represent the state. This is the state, which we have here, and that's going to be D. The T will come out. So we have I1 of T, I1 of T, I2 of T, I2 of T, and V1 of T, V1 of T. Is that okay? Then we now want to place the variables here. And now these variables are going to multiply the state vector, right? Which is I1 of T, I2 of T, and V1 of T, which is this, right? Then plus B. And we know that B is our output, right? And we have it here, isn't it? So then we have our B. We now multiply S of T. S of T. Now, afterwards, we now have our output, which is this, which is Y, which is equal to C. C being the output matrix, then is going to multiply the same state variables, I1 of T, or no, sorry, I2 of T, then V1 of T. Plus, well, D, in this case, is 0, the feed forward. So there's no feed forward. So it's a 0, okay? So this is similar to what we have here. So now let us look up our system matrix going by this expression, okay? Now, here we have I1. There is no I2. I2 is equal to 0 in this first expression. Then we have V1, which is V1, right? So we can now represent them. So the coefficient for I1 is negative R1 over L1. Now the coefficient for I2 in this first expression, in this first differential equation is 0. Now the coefficient for V1 is 1 over L1. Negative, right? Negative 1 over L1. Then we have B, which multiplies S of T. And we have that here, plus 1 over L1, okay? So we have 1 over L1. We are done with the first line. So now, for the second differential equation, I1 is equal to 0 because we have I2, so that is 0. Now, I2, the coefficient for I2 is minus R2 over L2. And then the coefficient for V1 is negative 1 over L2. Then B is 0 because there's nothing here, 0. Now for the third equation, now we have I1 and I2, so that'll be 1 over C, 1 over C. Then for V1, it is 0. And this is also 0. So we've populated that. Then we'll come to the output. This is the output. So we don't have values for I1, but we have value for I2. So that's 0. For I2, it is negative R2. Then for V1, it is 0. So we are done. So this is the state space representation of the circuit, of the RLC circuit that was given. So the next thing now is, what do we do with this? So we want to confirm if the system is stable. So how do we check for system stability? Then how do we check if the system is controllable or observable? Okay, so I think that's about it. So let us wipe this. Okay, well, let's wipe all of these. Let's just wipe this. So the next point now is for us to figure out a system stability. I want to confirm if the system, if the state is controllable. So I want to check controllability, observability, and we also want to check the stability. Okay. So, but before I move on, we have different forms of space representation. Okay, we call them the canonical forms. Okay, let me just mention it here. Let's say canonical forms of space representation. So we have phase variable canonical form. We have the controllable canonical form. Then we have the observable canonical form. We have the diagonal canonical form, and then we also have the Jordan canonical form. So these are the basic forms, you know, we could use for the representation of state space models or whatsoever. But what I want to mention, which is pretty straightforward, is the controllability, observability, and stability, okay, because of their application. Okay. So I want to quickly run through this. So when we say a system is controllable, what do we mean? So I need feedback from the class now. State controllability. What do we mean? Any feedback, please? So is someone talking? I can see Kelvin.
Good afternoon, sir.
Yeah, very good afternoon.
Yes, sir, my hand has been up for a little while now. I was about to ask a question on the previous slide.
Okay, what is it?
Yes, I wanted to ask why the feed forward matrix was 0.
Okay, because it's not in the equation.
Okay,
Yeah,
thank you, sir.
You know, the output at this point was negative R2 I2 of T. Okay, so that's where we stopped, right? So
yes, sir.
Yeah, so if it had the feed forward, probably would have had plus something blah blah blah, then that would have represented the feed forward component. You get what I mean? Okay, so what do you understand by controllability, Ibrahim?
Okay, but when the external is controllable, it means it is dependent on another variable or another system for it to function.
Okay. So I'll just document this. So we say that a system is completely controllable if there exists an unconstrained control, say U of t, that can transfer any initial state, say S of t naught, to any other desired location, S of t, in a finite time. Say t naught less or equal to t less or equal to t. Okay? So if we have a matrix, say C, which is, what's our C again? The output matrix, right? So if we are given the output matrix to be this, then, or better still, we can, let's not say the output matrix, the controllable matrix, please. Let's not call it the output matrix. Let us call it the controllable matrix. So how do I put that now? CM, let's say controllable matrix CM, okay? So how do we formulate the controllable matrix? Using our system matrix and the input matrix. Now, you observe that our controllable matrix and our observable matrix can be derived using our system matrix A, then input matrix B, and then we have the C as our output matrix, right? Output matrix C. But the controllable matrix is a combination of the system matrix and the input matrix. Okay? And then you now see that we have the controllable matrix to be, this is B, then we have the product of AB, then we have A squared B, then we have A cubed B, all the way to AN minus 1B. Okay? So once we have this, then if the determinant of this matrix, of this our controllable matrix, if the determinant of CM is not the same as 0, or better still, if the rank of the controllable matrix is equal to n, then we say that the system is controllable. Otherwise, it is not controllable. So what is n? I think that's one question that will come to mind. What is n? So n is the order of the matrix. So if we have a 2 by 2 matrix, then it means n is 2 for an n by n matrix. So if at the end of the day, you are resolving a 3 by 3 matrix, then the rank must be 3, equal to 3. If the rank is equal to 3, meaning we have 3 non-zero elements, not the rows, we have non-zero elements in the 3 rows of the 3 by 3 matrix, then we say the rank is 3. Now, if the rank is n, then the system is controllable. Better still, if the determinant is not the same as 0, we say that the system is said to be controllable. Okay. Okay. Israel.
Okay, sir. What if the rank is not a square matrix? Let's say it's like a 2 by 3 matrix. What do we say for that?
Well, you're going to see what we'll do right away. So we are going to be, at the end of the day, we are going to be playing with square matrix. Okay.
Okay.
Yeah. Yeah. We are going to be playing with square matrix, in our analysis. Okay. But you'll see shortly. Okay. But is this clear? Well,
Hello, sir.
Yeah.
Yes, sir.
Yes, sir. You mentioned output matrix before. Is there any relationship between the output matrix and this controllable matrix?
No, it's the observable matrix. I mentioned this when I said, the controllable and the observable matrix can be formulated using these. Observable and controllable matrices can be formulated using this. So the controllable matrix is formulated using the system and the input matrix, while the observable matrix is formulated using the output and the system matrix. Now, let's think about this intuitively. This is the input to a system. This is the output. Okay? This is the input. Now, this is the system parameter. Okay? Now, if I want to control this system, what should be of interest to me? It should be what I feed into this system and what is in this system. That is what I'll be able to use to control the system to get my desired output. Isn't it?
Yes, I understand now, sir.
Yeah.
Thank you, sir.
So if I'm not getting a desired output, then I may have a feedback. There's no problem about that. But should I have a feedback, meaning whatsoever I got as my output, I'm sending it back to the input. The bottom line is that becomes my input to the system to control whatsoever is happening here. So the system matrix itself and the input matrix is of interest when we are trying to control. But what about when we are trying to observe? So then I want to observe from my output. I can't observe from my input because that's the excitation. I want to observe from the response. So if I have to observe, then I have to observe my output based on the interaction in the system, right? So that brings us to system observability. Okay, so we say that a system, like we described earlier for controllability, is completely observable if and only if there exists a finite time, say t, such that the initial state, say S of naught, can be determined from the observation history y of t, like I mentioned earlier, given the control u of t over a finite time interval. Okay, so we now say that the observable matrix can be formulated using the output matrix and the what's it called now? The system matrix, right? So let me wipe this. No. Let's say A. So this could be CA squared all the way to CAN minus 1. Okay. So I could put it in a row, but I'll put a transpose, right? So in the same vein, when the determinant of the observable matrix is not the same as 0, or better still, the rank of the observable matrix is the same as n, then we say that the system is observable. Is that clear?
Yes, sir.
Hello, sir.
Yeah, go ahead, please.
Yeah, I'm trying to disturb one more time, sir. Sir, why is this observable matrix a column vector and the other one we discussed was a row vector, not a matrix?
Okay. Okay. So we are going to play with an example then. So I think things will get clearer. Is that fine?
Yes, sir, it is, sir.
Okay, so let's just play with one numeric example. Okay, let's do this. So we have the state space representations is 0, 1, minus 6, minus 5, x plus 0, 1, u. And then, okay, this is what we've got. Okay, so we have A, we have B, right? So with this, we can do controllability, right? Isn't it? Hello?
Yes, sir.
So
Yes, sir.
now for this, we know that the controllable matrix will be B, AB, all the way, okay? But this is just fine for what we want to do. So we know B, right? So we know A. So AB will be equal to what? 0 minus 6, 1 minus 5, 0, 1. So this will give us, once we multiply this by this, then add it up this times this plus this times this, that's 1. So this times this plus this times this, that will give us what?
Minus 5.
Okay, minus 5. But this is 0, right? Good. So we already know what B is. B is what? 0, 1. And then AB is 1 minus 5. So this gives us our square matrix. Okay? And we have this first row contains non-zero element, and this second row contains non-zero element. So the rank is equal to 2, right? So how about the determinant? Let us find the determinant of CM. This times this is 0 minus 1 is equal to minus 1. So it is not equal to 0. So it means that this system is controllable, right? Is that clear? Is that clear?
Yes, sir, it is, sir.
Yes, sir.
Okay, so do we still need to play with any other example for controllability? Observability, I don't think. The same system applies, okay? Because now all we know is that
display.
What's that?
Sir, please show for observability.
It's the same thing. We are actually literally playing with the same thing. Say this is the same as 0 minus 6, 1 minus 5, for instance, plus that u. Then the output y is the same as 0, 1, x. This is x, please, plus 0 u, right? So there's no 0. Now we know that for observability, we need A and C, right? So the observable matrix, OM, is the same as C, CA, right? That's what we have here. So we have C, which is 0, 1. So we have C. So CA will be 0, 1, 0 minus 6, 1 minus 5, right? So that's going to give us what? This times this, that's 1. And this times this, that's what? Minus 5, right? So the observable matrix will be the same as C is 0, 1. And then this is 1 minus 5. So once again, the rank of this is 2, right? And then the determinant of OM is the same as what? Minus 1. That's 0 minus 1 minus 1. So it means that the system is observable. Okay. So there's one thing I want to mention here. Yeah, go ahead, please.
So there's in that matrix OM, there's 0 at like the, well, I say the leftmost corner. So
This?
why is the rank? No, like down OM.
This?
After our place, there's 0 this side, that upward side.
But the row, we are looking at the row, the complete row. It contains non-zero element.
So if even though it has 0, as far as it has like another number apart from 0, it should give you rank 2, right?
Or better still, we could remanipulate this again by row transformation. You could perform row transformation again if you want to ensure there's non-zero value. Okay, so you can perform row transformation, okay, when you go back to your matrices. I'm sure that's clear.
Thank you, sir.
Okay. Okay. Now,
So,
okay, go ahead.
yeah, for the controllable matrix,
Mhm.
give us that formula of the matrix B, AB, A squared B, and so on. So where would
I
you,
didn't get that. I didn't get that.
for the formula of controllable matrix, give us
Okay.
that B,
The
AB,
controllable matrix, right? Mm-hmm.
yeah, it's the matrix B, AB, A squared B, and so on. So
B,
where would you know?
AB, A squared B, A cube B, all the way, right?
Yes.
Mm-hmm.
So where would you know the place to stop?
Where to stop? It
Yes.
depends. It depends on the dimension of your matrices. So from your system matrix, you can tell. So if you look at what we played with 2 by 2, right? The examples we played with, they are 2 by 2 matrices. So from the system matrix, you will know. Okay?
Okay.
Yeah.
Yes.
Okay. Okay. Now, so with this, you now see that having your system is not enough, but analyzing the system is very, very important. Okay, so you want to synthesize the system, you want to design a system. So you also want to check for stability, you want to check for controllability, you want to check for observability. Now, this is the simplest perspective we can give to it. But as you progress in your system or study, then you begin to, play with more advanced tools. Okay, so controllability in general provides how a system responds to different input. Okay, so just to recap, so we say that controllability provides how a system responds to different inputs. Okay, so we're observing, we are looking at the system interaction with the input, so it helps in providing a flexible system response. Okay, now also controllability, or better still, let's just say a controllable system. Okay, a controllable system can adapt to changes when the operating conditions are changed. Okay, so it helps with that. Then how about observability? This helps in the precise control and monitoring of the system, okay? So we want to accurately estimate the state of the system. So observability also, checks the internal behavior of the system, which helps in detecting faults, okay? So it also helps in fault detection inside the system. So like I mentioned earlier, in terms of application, I made mention of aerospace, space engineering. So when we say controllability, it ensures that the aircraft can be moved to different locations from a specific site, right? While the observability in this case will help in the accurate estimation of the navigation. So you can also talk in terms of robotics, okay? So controllability will help in providing the precise control of the robotic arm, for instance, the motion of the robotic arm, while observability will help in measuring the state estimation for mapping, okay? Just like observability helps with navigation, okay? Then in power systems, you see that the controllability helps in regulating the power flow, while observability will provide accurate monitoring and control of the system, okay? Now, these are two major aspects, hyper stability. So if, for instance, we are given an LTI system described as with this differential equation, S of t, then, or better still, we can look at the time advance of this is the same as AS of t when the initial value is the same as S naught. So we can now measure, or better still, talk about three forms of stability, okay? We say that the system is asymptotically stable if S of t tends to 0 as t tends to infinity, given the initial condition S naught. Now, it could also be marginally stable if S of t does not tend to 0, but remains bounded, okay? As t tends to infinity for all values of the initial value. Then we now talk about the system being stable if it is either asymptotically or marginally stable, okay? Then from the above, we can say that a system is unstable if it is not stable. That sounds really simple, right? So that is, if we take the norm of S of t, it should tend to infinity as t tends to infinity, at least for some, if not all, of S naught. Okay? Well, when we talk about transforms, we'll play with some other forms of stability and the likes. Oh, now we're supposed to cover impulse response today. So, and we've got just a few minutes. So any question for now? So we know if we have to move the impulse response to our next class, but you have the lecture note online, so you want to cover that. But before we call it a day. I think I would love to just mention a little detail about convolution. Okay, but we have Shobayo. Go ahead, please. Convolution. Okay, Shobayo is not talking. It's fine. So,
Yes, sir.
okay.
I said, where can we get the lecture notes? Online, where, sir?
Where what?
Where can we get the lecture notes?
I can't hear you. The line.
Where can we get the lecture notes, sir? Online, where?
Yeah, well, I'm going to upload this too. I'm sure you have access to all the lecture notes on YouTube, right?
Okay, yes, sir. Yes,
Yeah,
sir.
so that's fine. I'll try to upload
Sure,
this.
sir. Sure, sir. Can you hear me?
Go ahead, please.
I just want to clarify. This will also be part of the series on your channel, right?
Yeah,
This
sure.
particular lecture.
Yeah, sure.
Okay, thank you, sir.
It's part of it. Yeah. So I'll try to upload as soon as possible. Okay. You have nothing to worry about. At least you should.
And sir,
Yeah.
in case I plan to play with more questions, is there any particular material you might recommend I go to, or do I just check randomly on the internet?
Well, do you have the teaching plan?
I should, sir.
Exactly. So I think some textbooks were recommended alongside the channel, in the teaching plan. Yeah.
Okay, sir. I'll check it, sir.
Oh, you're welcome. So let's assume we have a system. Well, we've been talking about how to control the system, how to observe it, and how to check if it is stable. And we feed it with some input parameter. Then we should get an output y of t. But we know that the LTI system is described by the impulse response, because the input to this LTI system is the Dirac, let me just say, well, the Dirac delta function. Okay. Now, the point now is this: the output of this system is going to be the input S of t convolved with the response, or better still, the parameter that describes the system, which is the impulse response. Okay. Now, for ease of analysis, okay, this impulse response, h of t, in the time domain will be better estimated in the frequency domain, okay? So that we now have to begin to think in terms of transforming h of t to h of s, okay? Such that h of s will now be referred to as the system or the system or transfer function, while h of t is the impulse response. So in the time domain, we talk in terms of the impulse response, but in the frequency domain, we talk in terms of the system function or the transfer function. Okay?
Yes, sir.
Good. Now, we already mentioned how the Dirac delta have a unit value as it tends to 0 in our lecture note. So I want to just move on, okay, with our process. Now, we already know the import of the Dirac delta function, okay, which has a unit value, okay? Now, should we shift, or better say, perform time shifting of this function, okay, like we already mentioned, say Dirac delta t minus t sub k, then it will shift by that amount of time, 1, okay, t sub k equals 0 in time. Okay, now the idea is this, that if we multiply a signal by the time shifted Dirac delta function, then that particular signal is going to take on its value at that location. Okay, because the Dirac delta function, t sub k, is the same as a unit value, okay? So that this signal will be s of t sub k times 1, which will be equal to s of t sub k. Okay? So this is what we use for signal sampling, say, where we have to now sample this signal at different time intervals, say t sub 1, t sub 2, t sub 3, all the way, okay? So that the value of this signal at t sub 1, say s t sub 1, will now be the same as s t sub 1 times the Dirac delta t minus t sub 1. So s t sub 2 will be the same as s of t sub 2, Dirac delta t minus t sub 2, not t sub k. Now, all the way to t sub s t sub k will be the same as s of t sub k, Dirac delta t minus t sub k. Okay? Now, when we add up all of these signals, it will give us the output. Y of t will be the same as s of t sub 1 plus s of t sub 2 plus all the way to s of t sub k. Okay? And this now will be the same as s of t sub 1 Dirac delta t minus t sub 1, rather, plus s of t sub 2 Dirac delta t minus t sub 2 plus all the way to plus s of t sub k Dirac delta t minus t sub k. Now, since this is a continuous signal, this will not be the same as integral. Now we have up to 3 from t sub 1 to t sub 3 will be s of t sub k Dirac delta t minus t sub k dt. Now, this expression is the convolution in time domain. So you observe that it is the sum of the scaled and shifted component of the signal. That's where I'm going to, okay? So when you hear the word convolution, what we're actually saying is that this is the sum of the scaled and time shifted components of the signal. Okay? So that in a more general form, y of t will be the same as negative infinity to positive infinity, s of tau delta t minus tau d tau. And in the discrete domain, it will be sigma negative infinity, say k equal to negative infinity to positive infinity, s of k Dirac delta n minus k, where s of tau and s of k are the shifted, are the scaled, rather, scaled. Sorry, they are the scaled components. Y delta t minus tau and delta n minus k are the shifted components. Okay, I think this is a good place to stop because we are just in time. So any questions so far?
Yes, sir. I'm a bit confused, sir.
Confused about what?
It's on the previous page, the one before this one. The place where we have x or x bracket t and the delta sign t minus tk. How did it convert on the right-hand side of the equation to x bracket t sub k? I didn't really get that part.
Well, I still don't know what you're talking about, but let's see if I can take this back. This will take a little time. Sorry, we just are going to take 1 or 2 minutes of your time. Let's take this back. Okay, are we there?
Yes, sir. Yes, sir.
Okay.
The x bracket t, the direct delta sign t minus t sub k equals to x bracket t sub k close brackets. Like
Are you
how
talking about this or this?
Yes, this on this page, at the top.
This?
Yes, yes, yes. I don't understand how it's transformed. I'm a bit confused.
Okay. So I think you have some time to spare, right? Okay, let me just quickly run through this. So now you know your delta function means that it is infinite at t equal to 0 and is 0 otherwise, right?
Yes, sir.
So it means that at 0, it extends to infinity. Okay?
Yes, sir.
Now, it
Yes,
is a
sir.
unit value. It means that the area is unity, right? So
Yes,
if
sir.
for
Yes, sir.
instance, y of t is equal to say 1 over 2a and this 0. So let's take on values from negative a less or equal to t less or equal to a, then otherwise. Now, if we estimate this area, so what are we going to get for this rectangle? We have this. So we have negative a to positive a, and the amplitude is 1 over 2a, right? So this t.
Yes, sir.
So the difference here is 2a, right? Length times breadth. So that will be 1 over 2a into bracket 2a. So this will truncate this, so it's equal to 1. So the area is 1, right?
Yes, sir.
Now, if we also take the integral of this, we'll find that it's also 1, okay? Y of t dt. So that's integral negative a to a 1 over 2a dt. So if we integrate this 1 over 2a into bracket t, negative a to a, right? So at this point,
yes, sir.
Okay, I'm coming. So it means that 1 over 2a into bracket a minus minus a, that's 1 over 2a into bracket 2a, so that's equal to 1, right? Now,
yes, sir.
if we should reduce this by half, let me change the color so we don't get confused. If I should reduce this by half, where this is now, say, negative a over 2, and this is a over 2. For us to be able to get unit value, so this will have to scale up, right? Because this
Yes,
will have
sir.
to be 1 over a. So that 1 over a into bracket 1 over a minus 1 over a will be a. So that will also give us unity. So as I'm scaling this, as I'm reducing the width, we realize that the height is going up. So when the direct delta function is now having a width of 0, we observe that the height extends to infinity.
Yes, sir.
Is that okay? But now,
yes, sir.
If that is true, then it means that a unit value of this direct delta, say k, for instance, is this. But what will happen if I perform shifting, time shifting? Now, recall that it is 1, right? The value is 1. So if I should perform time shifting, what will happen? It will only shift at this point, but the magnitude is 1. So this will be like TK, or let's say T1.
Yes, sir. Yes, sir.
Then this will be T2. This will be T3 if I'm performing time shifting. And this will now be T minus T1, right? This will be T minus T2.
Yes, sir.
This will be T minus T3. So you now observe that if I should multiply the signal by this parameter, this Dirac delta, is also equal to 1. So if I should multiply this shifted component by the same signal, all we will see is that that signal value remains, only that it has shifted in time, but the magnitude of that signal remains the same.
Yes, sir.
Yeah, that's what happened here. So that this is my original signal. I have multiplied it by a time-shifted component, but we already know that this time-shifted component is the same as 1. So it's only shifting it by the amount of time delay, but the signal is the same. Only that that signal is now shifted to the new time scale. That's the beauty of the Dirac delta function. So I don't know if that explains, because this now is used for signal sampling, because we want to sample the signal, but we don't want to alter the content of the signal. So we now begin to look at the component of the signal in different time domain location on the time scale. But mind you, that Dirac delta function does not alter the signal in terms of its magnitude, because the magnitude of the Dirac delta function is unity.
Yes, sir.
Yeah, it's only shifting the signal. Is that clear?
Yeah, so sorry, just one statement, sir. So in essence, like in summary, are you trying to say that the shifted component is not affected? What is affected is the time scale of the scaling component.
Well, I don't get what you just said. Please explain.
Like in your lecture videos, you said X bracket TK is the scaling component, and Dirac delta T minus TK is the shifted component.
This is like scale. This is the scaled.
Yes, the scaled and the shifted. So I'm like, in essence, are you trying to say that when two of them are multiplied, this shifted component is not going to change, only the scaled component will be shifted?
Exactly.
According
that signal is only shifted relative
thank you very much, sir.
Yeah. That's why if I should sample a signal now, so if I should sample this signal, bam, bam, bam. Now, what I'm now going to get is 1, 2, 3, right? So what we are saying is that once I add this together, I'm going to recover this signal. Okay? Because these are now the scale components. So now this scaling parameter, this shifting parameter imposed by the Dirac delta function does not alter the composition of my signal, but I'm able to localize my signal. I don't know if you get what I mean.
Yes, sir.
Mm-hmm.
Yes, sir.
If you mix white and black, it's going to turn gray. But I'm saying, well, if you mix this with white, it's going to be white. If you mix this with black, it's still going to be black. Okay? It's not going to,
yes,
but at some point, we'll be able to recover it by adding it all up. So that's what we call convolution. Okay, so at this point, well, I want to apologize for taking your time. So do have a great day. I hope to get your feedback on the appropriate model you want to adopt for your quiz next week, because we do not intend to have a Zoom meeting next week. So we want to assess what you've been doing so far. So as soon as I get the feedback, then we'll find a way to put the question forward for next week. So the very best always.
So please, how about the recording of the class?
The what? Yeah, you're going to get it. We're going to upload this, okay? Nothing to worry about.
What's be the format of it?
Well, you're going to know next week, okay? Is that okay now?
Yes.
Sir, please, how many marks is the test?
Oh, that's, I think there's nothing to worry about when it comes to grading for now, okay? But you'll be fine.
Okay, sir.
Okay, the very best.
Thank you, sir.
Okay, sir. Thank you,
bye.
sir.
You're welcome.